Swayam Prabha. Digital India. Educated India.
So today's class, we'll look at this microcontroller interfacing, specifically the PWM interface. So last class we have already seen some kind of a basic philosophies of this interfacing. Now we'll go a little bit more specific into the aspects of somewhat hardware kind of aspects at more like a philosophical level, in not really talking of all the details of the things, but to get you the concept, like how do we think through the way things can be implemented in microcontroller. Okay, that is a kind of idea that will slowly evolve. Okay, so let me clear this window. So let's begin with that. So as you all know, this PWM central idea is pulse width modulation. Just to kind of flash this thing to make sure, you're recollecting your memory that okay, PWM has this kind of a feature. It has some kind of a time period and some duty which is one can change that in operation. So this is how you see basic PWM signal. Now we want to generate such signal, and what is a way one can think of in microcontroller to generate such kind of signals. So there are mainly two parameters here for PWM. One is frequency and other is a duty. Okay, so the frequency parameter usually is fixed parameter, and the duty is what changes continuously. Okay, during operation, you want more power to be delivered depending upon what your control input is or control computation is, then you will change this PWM duty cycle, and you can see here the signals for different duty cycles, how they look like. So this is a 0 level here, and this is 1 level here, and 75% of the time this the on time is 75% of the total cycle time. And then that's how you drive some kind of average voltage into the application. So that's what would happen. Now we already have talked about this, why we need PWM and all these details. If there are advantages because it is a digital signal and there are no noise effect that would come. I'm just reiterating some of these things that we have already seen. Now the question is how this PWM can be generated by a microcontroller. Okay, so we start off with a microcontroller clock. So PWM signal is some kind of a periodic signal. So clock is the best thing to kind of begin with. So the clock's frequency is, if you scale it down, you'll get a PWM signal. Okay, or you get some kind of a frequency controlled signal of the clock. Okay, or frequency controlled clock. Okay, or clock at PWM frequency, like that. But would that have is that sufficient? So say for example, you start off with the system clock and scale it down. See here, you can see that this is a system clock coming, and I have here 4 kind of a clock pulses covered in one cycle. So I just put some kind of a scaling factor of 4 and I get this PWM clock signal. Okay, so this is one of the ways to kind of produce the clocks or produce some signals which are at a lesser frequency than the clock frequency. Okay, you use some kind of a scaling factor. Now how that happens at hardware and all, we are not getting into details. Now the question is, once you have this, say, some kind of a clock signal for PWM, then how do you kind of get a duty cycle for that? So that is what is. Can you think about, like, just a minute, I will pause here and think about it, and then, like, you proceed. Okay, you can pause here and think about. Suppose you have this PWM clock signal which is running at a frequency which is some kind of a clock frequency for PWM interface. This is not really PWM frequency. So we want to kind of get two things. One is a PWM signal, PWM frequency out of this PWM clock. So PWM clock will typically be running at very high kind of a frequency. So system clock, for example, in Tiva is 80 megahertz. So PWM clock will be scaled down maybe by a factor of 4 or 6 or 20, 32 or some factor. Okay, so that will generate PWM clock. Now using that clock we want to kind of get our PWM frequency and somehow the duty cycle. Okay, can you think of a way to do that? So see, because if we just scale this clock further down and get PWM frequency clock signal, that will have a fixed duty, that will have 50% like a duty cycle. So scaling may not be a way directly, because scaling will kind of give you only a 50% duty cycle value. So let's proceed with and see now what is that we can do. Okay. So here you can see that this is now PWM clock signal. So this is like a already scaled kind of a clock signal. So I have drawn this scale in a different kind of a manner here. So our clock signal was looking like this, but now our PWM clock is looking like this. Okay, so this kind of time scaling is done here to kind of illustrate the aspect. So now you start off here with a counter which is, say, counting pulses. Okay, so it counts 1 2 3 like that, it counts, and it counts with, say, 10 pulses, and then you do something. Okay, you say, okay, that is your period for PWM. Okay, so the PWM signal clock period will be something like a 10 counts of the clock here. Okay, and then further if you say, okay, my duty will be out of this 10 pulses, duty will be 3 pulses. Okay, so then I can get a 30% duty cycle kind of a value. So I need these two numbers once we have a PWM clock. One is the value which will be corresponding so this is somewhat the kind of a scaling factor, you can say. I count this many number of cycles to generate one PWM cycle. Okay, so 10 PWM clock cycles will give one PWM cycle, and out of that 3 counts or 3 cycles will correspond to a particular duty. Okay, so here now, since I am using this number 10 here, my resolution of PWM, can you think what is the resolution that is happening here? The resolution here, you can see that I can have only one clock cycle as a duty, as a minimum count for the duty, and that will correspond to, out of the 10, 1, that means it is like a 10% resolution. So I cannot say I want a PWM signal of 5% duty cycle. No, I cannot produce with this particular kind of a thing. For then what I'll need to do is I'll need to kind of increase this factor. Okay, so this is a very important understanding of basics, that okay, look, if you want higher resolution, what you are supposed to do. So if you want, okay, so given some kind of a scenario, and we say that in this scenario I want best possible resolution. Okay, what should I do? So I need to kind of then have this PWM clock frequency a much higher value. Okay, so if it is higher value, then I'll have a lot of numbers. Okay, because PWM frequency of PWM is fixed, given by the application. So to have more cycles in the same kind of a period of the PWM frequency, I'll need a PWM clock frequency to be higher. Okay, so like that one can start thinking. Okay, so this is a basic kind of idea. Then you can have additional controls, that okay, you have left or right justified signals, or this signal is delayed by with respect to some other signals and things like that. Okay, then counter can be only counting down or counting up, or all those kind of things can be possible. So this is counter loaded with 10. Now this 10 can be counted up or counted down, and then depending upon that something will happen. But basic concepts is basically these for getting the PWM signal produced in the system. Okay, so for programming, if you go into now a little bit more programming details, like there are two methods. So again, we have talked about this philosophically in general, but with respect to Tiva also, you can have direct programming by control registers. Okay, this XCP 100 code we write based on, like, the registers. So you fill in these registers with some values, okay, and then, like, something will get executed. So there are these two types of registers that we have seen, control registers and working registers. For each interface there will be some control registers which need to be initiated, or for configuration they are just initiated once, and then working registers are maybe getting continuously updated by, say for example, in the PWM case, PWM frequency is fixed, so it is a part of that control register setting, and then working register is PWM duty, which is changing as per the control computation every sampling instance. Okay, so that will be like a working register. And then second philosophy of method of having the programming done is using API or library functions that are already defined or already given by this TivaWare. So you have seen that the TivaWare library has a lot of these functions written, like the header files, some variables are defined, and then some functions are written as functionalities can be directly used. Okay, so there is a manual which gives you the details of how these functions are, and which is already posted to Moodle. Okay, so some of these functions are also defined in the ROM of a Tiva for execution, which is going to be very fast. Okay, because then, like, the compiler will not have to fetch these functions from your hard disk and then compile and dump this entire compilation to Tiva memory. You'll save some memory if these functions from the ROM are directly used, because they are already there in the read-only memory part of the Tiva board. So if you are starting using those functions, then you don't need to kind of download these functions again during compilation and put them onto the Tiva board or memory of the microcontroller. So we will focus on second method, but we'll get into some kind of insights into how this module, particularly in Tiva, is configured or working. So you can understand, we'll not get into control and working registers in detail, but just get a kind of a feel for how this is really done in Tiva. So Tiva, if you see the data sheet, you'll see that it has two PWM modules, PWM 0 and PWM 1. Correspondingly, there will be pins which are named, and each module will have 4 generators, generating 2 independent PWM signals. So how many total PWM signals will be there? 16 PWM signals can be generated then. Okay, so 2 modules, 4 generators, and each generator generates 2 signals. So 8 signals is will be generated by one module, and you have 2 modules, each module has 4 generators. So you have 16 PWM signals that can be generated. And although I must caution you that all 16s may not be available for the Tiva launchpad that we have been working with, because only some few signals will be available for programming different interfaces, because otherwise there will be too many pinouts that have to be done on the board, and that will be too cumbersome for the board. So there's some kind of a base minimum functionalities that they have provided out. Although the chip that is there existing on the board will have all this capacity, but the hardware pins that are gotten out from the board will not be all the pins. Okay, there will be some selected pins have been gotten out. Okay, so then each PWM generator has all these kind of features. Okay, so you can read through these and see if these things can make sense. Okay, So how do you kind of make sense of these things? Okay, so you to make sense of some of these write up or functionality details, you need to refer to the block diagram. Okay, this is a block diagram of this. You see this PWM generator block. Okay, so this is a block diagram for this PWM generator block, and in that there are these different kind of components here. There is a timer, there is a comparator, then there is something called signal generator, and then deadband generator, and then you will get your PWM signals out for this particular generator block. So so each module, you remember, has 4 such generator blocks. Okay, we are just looking at one generator block which will generate these 2 PWM signals A and B. Okay, and input it will take as a PWM clock. So by seeing this diagram, you should think, what you can do, what you cannot do. Can you think about that? Pause a moment and think about, okay, what you can do and what you cannot do. So one can see that the PWM clock is same for one particular PWM generator block, or for that matter this clock may be going in other blocks also in the same way. Okay, so you cannot have independent clock for these PWM A and B signals. Okay, so the PWM clock will be same for both the signals, or for that matter all the generators. Okay, so like that one can start kind of concluding some things. Then there is some kind of a timer which will do some further kind of a timing for this clock, and then there will be comparator which will, so we will see how these things work. So the signals will go typically this is a flow of the signals. Then we start with the timer, and then the signals will go to comparator, or some timer signals will also go to the signal generator, and then from comparator you have these 2 outputs coming, compare A, compare B, and they use some kind of a timing part here also, and produce this PWM A and PWM B signals, and then those signals are further processed by this deadband generator block, and here, so this is a kind of a signal flow is what one can understand. So like that you can think about, and you can have your own conclusions drawn. Some of these conclusions I have written in the next slide. Okay, I need to get this pointer again here, so you can read through some of these conclusions. Okay, so PWM signals can have independent frequency, or PWM A and B signals that are coming, they would have if the count is specific to the channel. So you need to check whether there is a count for the specific channels, same count is given for both channels, something like that. You check that data and you will be able to kind of see, okay, this PWM signal frequencies can be changed by changing the count for each specific channel. Okay, so these are some functional description that will be given. So these are directly taken from the data sheet, and you can see whether these things make sense to you. Okay, so you can read through. So this is just to kind of give you some feel of typical interface will have this kind of description, and how do you make sense of this description to see, okay, how things are working inside internally. Okay, say for example, if you are directly focused on APIs and functions, you may or may not need to know so many details. Okay, you will be able to kind of program even without knowing these details. Okay, but we need to know some of these to do little finer programming. Okay, so once you have some things going, you want little more finesse of control over signals that are generated. You need to understand this and then see, okay, what is possible, what is not possible. So if you understand, for example, there is this modes of timer which has count down timer mode, or count up and down timer mode. Okay, so in count down mode it will only count down, and then at the end of the count, then okay, or wherever this count becomes 0, it will again load the same value, and again start counting from that to 0. Okay, so these kind of things is one kind of a mode of operation for timer. Other mode will start off with counting up, and then again count down, again count up from 0, and then again count down. Like that it will start. So how do they use this further? Okay, then it will have some more kind of a details that are given. Then there is a direction signal for counting up and down. So this signal will be useful typically when we are doing count up and down mode, so that you know which is the direction going ahead with, so that signal will be coming out of the block. So if you see, there will be some direction signal coming out of the counter block somewhere. Yeah, see, this is a direction signal, okay, from the timer. Okay, so like that you can look at the diagrams with respect to the description that is given. So let us now get into a little bit more kind of a meaning of some of these things in terms of how things happen inside the timer. So this is like, this is like, functional description for different blocks. Now we are going through details. Okay, and first is a timer block, and timer block has these two modes of operation, and then there is a comparator block which will keep, like, whenever this count happens to be the value which is given in the comparator block, then it will produce some kind of a pulse. That is what is a function of comparator block. This will be more clear when we see the actually the figure of this. So we are looking at these two blocks, timer and comparator. They are typically working in sync with each other. So timer keeps on, like, giving the count, which is kept on reducing as for every PWM clock cycle. Okay, so PWM clock cycle ticks and the counter reduces by 1. Okay, next tick, counter reduces by another value. Like that it keeps on kind of decreasing the successively the value of the count, and when the count becomes equal to, say, this PWM compare A signal, then some kind of a pulse will be produced on this compare A output, and like same thing will happen with this compare B output. So what is the signal that will look like on these lines? Is that what we will look now? Okay, can you think typically, suppose I am having a down timer, then, like, if I say when the count down value becomes equal to this particular value PWM CMP A, then I get some small clock pulse on the on this compare A signal. Otherwise this compare A signal is going to be 0. Given this description, can you think and plot, for example, how these signals are going to look like? So that is exercise you can do, pause and do a little bit, and then move on to the next slide. Okay, so this slide now actually gives you this data. So this is a value that is loaded, some value which is loaded in the counter, and it starts counting it down. Every clock cycle, one countdown will happen. Okay, and then it goes to 0, and again it starts loading the same value. So this is like a countdown mode only. Okay, you are not counting up anytime. You are only loading the fresh value and again counting down, loading fresh value and again counting down. Okay, so the similar kind of a thing happens when we go for the count up and down, where here now you will have a count up first. You reach the load value, then you start counting down. So these signals are going to look like that. Now whenever this compare A and compare B values are hit by during the countdown process, of course for that compare A, compare B values have to be lesser than this whatever value you have loaded in the counter. Okay, if it is more than that, I mean, there will be some error that will be popped out, or it may consider the highest value here. So we don't know what is, that must be we need to see through the details of the datasheet to kind of see what happens under such scenarios. Now what happens when this compare A signal is reached by the counter, the CMP A, on that signal you will get this little pulse, clock pulse, and same thing happens with compare B signal. Okay, on the compare B signal you get this little clock pulse, and now these clock pulses are used further for processing and generating PWM. How that happens, we'll see that in a minute. But you can see that Similar kind of thing happens with the PWM countdown. So wherever this counter hits on the up count, it will generate pulse, and on the down count also it will generate pulse on this CMPA, CMPB signals. These are the kind of signals that will be getting generated. And then this is a direction counter. So this is a direction, counting up is positive, and then counting down is 0. So that's how, like, these things work inside. Now you are using this further in this block, which is signal generator block. Okay, so these signals are going into signal generator block, and this signal generator is using, like, some of these and converting that into this PWM A and B signals here. Okay, so how that happens you can see here. Okay, so maybe you can pause and think and, like, see, okay, what can be done. Say for example, if you have these kind of pulses coming, okay, how can I kind of generate PWM out of these pulses? So say for example, this load corresponds to, like, some kind of a frequency. Okay, that could be my PWM frequency, and then this compare a value, whatever I am writing, that can kind of give you some kind of a handle over what should be my PWM duty cycle, things like that. So one can think about that kind of a logic to do the signal generation in the signal generator block. Okay, so you can see here what is happening now in Tiva. So you can see in signal generator, like, whenever this compare B is reached, like, B signal, that pulse now is getting converted into a trigger which will make this PWM B signal go high. Okay, so this value is low, this signal goes high. Okay, and when this same value is reached on the down count, then again this value is made low. Okay, so that's how, like, these compare A, compare B signals work and produce PWM B signal in the signal generator block. Okay, so those little pulses that are produced by the comparator block are used in some way to create some kind of a logic circuit which will get this PWM signal B out in such a way that moment this value is compared matches, count value matches, PWM B signal is, like, made high. Same thing for PWM signal A. Whenever the value matches from 0, the PWM A signal will be turned to 1, and then whenever on the down count the value matches, this signal will be turned to 0. Okay, if this is a logic is used, now you do an exercise. Now same logic, if it is happening for the sawtooth waveform, which was, like, count down signal only. So this was a count down kind of a signal only. Then what is going to happen? So you can think about that. What kind of a logic needs to be there such that, like, this compare A value will be somewhat changing this binary signal from 0 to 1 or 1 to 0 or whatever. So you think about that and, like, think what kind of a logic can be there. Okay, so we'll leave it right now. I'm not kind of going to explain you that, but using the same, extending the same concept, one can think about, okay, what will happen to these PWM A and B signals in the count down mode alone. Okay, and that's what probably we'll be using for our PWM generation. Okay, so that is what is that we need to think about. And then there are these additional facilities that, okay, deadband generator. Now, suppose you want to kind of have some deadband introduced in the signal, okay, at the start or falling edge of the PWM signal. Then how do you put that? So normally, if this is not enabled, this signal directly comes as output PWM A and PWM B signals. Okay, so for one generator you get now, like, this complete flow from timer to comparator to signal generator, and then your actual signal out. So this particular part will not get into more details here. There are some things which probably we may not be needing to use, but you can kind of go through the data sheet and, like, a little bit kind of understand how this control and the interrupts in PWM work. the fault conditions also can be displayed. So you can go and look at those details if at all you are interested more into that. But we may not need that PWM interrupt kind of a mode of operation of PWM. Okay, what we want to kind of do is generate these PWM signals and be able to control the duty cycle continuously, so that we can deliver in the actuator in mechatronic systems right amount of energy that is needed. Okay, so this is a deadband generator. A little more details about you can go through. So if it is disabled, then you don't have this shifting of the signals happening. But if there is a enabled, and then they depend upon the value that is given in some registers, you will have some delay produced in PWM A prime signal, which is the actual output of the PWM. Okay, so these signals will get delayed a little bit. So this is this part is called a dead band. Okay, you can have a rising edge delay or you can have a falling edge delay, and you can produce these signals. Okay, so this much understanding, along with some kind of a particular knowledge of some registers. So this register knowledge will be given in this. If you see this data sheet. Okay, in the data sheet you can get all the gory details about, say, registers. Say for some examples of these registers from the block, you can take and from this previous block diagram, and then search for those names. You'll get these register details. Okay, so you see this master control register. So a lot of many different registers will be there, and each register's all the details will be given. Okay, so this is like a register map. All the registers are given here. Okay, so you can go through these registers and make some familiarity. Okay, if you directly want to use these registers and program, great, you can do that, thinking, okay, all the course, if I understand all the registers, now that I understand this main philosophy, if I further understand the register details, I'll be able to control this register based programming, or I'll be able to generate this PWM signal at the register kind of a level. Okay, this is how we will go about programming for the register level. But so we'll do the programming mainly in APIs to begin with. So later we may not need also to get into the register level programming, but maybe as a part of some academic exercise, we can take some simple thing to program by using the register level details. Okay, so that we have that kind of a grip over the programming of this microcontroller. Okay, so for now, for typically for using this API or library for programming, we'll need to do something. Okay, some process need to be followed, or some steps need to be followed. Okay, so we'll look at those steps now. Okay, these other block details I'll leave it to you to kind of go through and understand if at all the situation or needs comes in your project. This may be useful. So these are the typical steps that are there for the programming with library functions. So you need to make sure that these header files are there in the library. Okay, so in driver library you will have pwm.h and pwm.c files. They'll be there, and they'll initialize a lot of variables that are needed for this. So the register level programming you'll need to know some of the base addresses and the values of the hardware register addresses, which will be already put in some of these header and library files. Then you don't need to know those detailed names and description. So you just need to know these are some of these functions, how they work, and things will be fine. So so this function description is given in the other file that is given to you. Okay, all these functions are given, their description is given. Maybe we'll see if we can figure out one of the such files. Okay, so let's see. here the Tiva functions here. Okay, so say here I have this pulse width modulation only. Okay, so this pulse width modulation, if you see this base, they have all API functions given, and then programming example also is given. Okay, so you can use that to get started with this. So see, this driver is contained in this pwm.c and pwm.h file. Okay, so there are a lot of functions. These functions directly reading those function details, you may not get to this procedure. So for procedural aspect, like okay, what functions to be used and like when or what is the sequence of using some functions, that is a little bit tricky to figure out. But you may be able to figure out based on the block diagram understanding that okay, I need to first initialize this, first initialize that, and like then do this, then do that. Okay, or you can see the directly here the examples that are given, programming examples that are given. Okay, that will kind of give you a better understanding. Okay, so here I'm just giving you more some kind of a detailed steps for the programming this PWM interface. So you need to initialize the hardware, so clock frequency needs to be set, and enable some PWM module that are to be used, and enable a port corresponding to the target PWM module. So these are kind of steps. Now I'll not give you like entire thing here, so you need to figure out based on some of these steps that are listed here and the understanding that is given in the PWM. So it's a little bit of a skill or art to master, like seeing appropriate information at appropriate place. See, if you start writing the data sheet or like the entire chapter on PWM, things will become too lengthy procedure, and you may not need a lot of such things. So once you are given a task that we have specified in our assignment 2, where you want to run a motor by using PWM. So to get to that task, you need to generate PWM signals on two signals. Okay, two pins actually, and one pin will be connected to one of the motor inputs, and other pin will be connected to other motor inputs. There are two motor digital inputs that are to be given for the motor driver. So the motor driver data sheet also will be uploaded on the thing. So these are different things. The important part here is like you need to configure this PWM module in there are many different kind of aspects of configuring. So configuring the clock, so we saw that block diagram needs a clock, so this is done by this command. Then you want to this pin size, this I was discussing in the couple of last classes also. Same pin is used for many different purposes in Tiva. So in Tiva or many microcontroller systems for that matter. So you need to kind of specify that okay, oh look, I want now to use this pin as for the PWM kind of a generation. So I say this is a pin as a part of GPIO, but I want to use it for PWM purposes. So that you need to specify somewhere. So that is where like you need to make the pins as pin type as like PWM pin. So once you configure this as a PWM pin, I mean you typically will not use this as a input output pin again in that application, because your hardware is connected to this pin now. Okay, so you cannot say okay, oh, I'll now make it use in my same program. Once sometimes it is used as a PWM pin, and sometimes it is used as a digital input output pin. That may not happen because your hardware is fixed there. Okay, so so you need to kind of make a choice of which PWM modules you need to use, or given the number of pinouts and what all application needs, you need to kind of make a choice of which PWM module you need to use and which kind of pin you need to configure as PWM pin. So those decisions are fairly simple. You will be able to see the pin maps, and from that maps you will be able to kind of match your application needs versus module which pins are available. Okay, then you need to configure pin for channels, different channels. Mm. And then so it's PWM generator configuration. So now you know what is PWM generator, okay, in the block. So in that you need to configure that PWM generator. So it will typically have whether this will have a count up or count down. Those kind of things will be somewhere specified. Mm. Oh, forgive me about this. This is PWM model. I'll change that. This is not QI model. This is PWM. All these are functions for PWM models. Set the period of the PWM. Then you enable finally the PWM. So like that you will have these different functionalities which are regarding the configuration of model, and then you need to have some functionalities which are regarding some output of the PWM. Okay, so like that you set the PWM period, you set somewhere PWM duty, and get your program going. So I'll leave you with this kind of understanding, and you can see now the example program and other things to figure out how things are really working. What are these each of these functionalities might be doing. Play around with the parameters and see how they are affecting your PWM generation signal, and all those kind of things. You can play around and do it yourself. Okay, so that's where we'll stop here now, and then what so further we are going to kind of we may look at a little bit like this, little more details about quadrature encoder interface as well, because these are the two primarily important interfaces for us to use from Tiva system. So we'll do this small kind of a presentation for quadrature encoder interfaces as well, and then we'll start off with the modeling part of the thing. And while modeling, we'll start exploring how these models really work in practice. So that is our future direction to go. So here we'll start getting basic understanding about how to run the motor. Once we are starting running the motor, then we'll have understanding about how to read the motor position by using encoders. So now we will get really high fidelity position output from the position sensor. Now we want to use this for further control. Okay, so this is how we will proceed. So before we going into control, we'll start sensing this position and use it for some identification of parameters of the system. Particularly, we'll look at friction identification in the motor system. Okay, so this is how this future direction is what we'll go with. Okay, so we'll proceed like that, and I'll stop here for now.